Assalamu alaikum everyone. Dear student, I hope you are fine and doing well. Today is our lecture, online 25th lecture of our course Introduction to Cryptography. Today we will discuss Paillier encryption algorithm or Paillier public key crypto system, or sometimes we call it homomorphic encryption algorithm. Dear student, the homomorphism is the property of two groups that preserve binary operations. But I'm not going a lot about the detail of homomorphism, but I just give you the some properties how a Paillier encryption algorithm is homomorphic. All those encryption algorithm which follows the homomorphic property all can be utilized in electronic e-voting system. Uh, Let us first familiar with this Paillier encryption algorithm. Ultimately, at the end of the lecture, I will give you one assignment that fundamentally clarify how you can uh, use this encryption algorithm to uh, understand the security of electronic e-voting. It's not what you call uh, electronic e-voting is something that is how you can perform electronically voting instead of manually. But this encryption algorithm is utilized internally in the mechanism of electronic e-voting in order to securely vote or securely poll your vote without any what you call eavesdropping or without any insecurities. So let us come up with the Paillier encryption algorithm. So it has basically it is public key cryptography then, and it is based on integer factorization based algorithm. It means to say we take any composite number and it can be divide can be written as a product of prime. Whenever I am saying IFP problem, it means to say integer factorization problem, and integer factorization problem I always mean to say any composite number can be written as a product of prime, two or more than two primes. So it's a public key crypto system. So the student, we can say it has three component: key generation, encryption algorithm, and then decryption algorithm. Let us define a key generation algorithm. So since this is based on integer factorization based algorithm, so it can be take any two prime number because these are independent of each other, means that they both are different. So takes is product and GCD of what you call this. Let me on this port line. So let this one. GCD of PQ comma P minus 1 Q minus 1 must be 1. This property basically assures if we both prime are having equal length. So compute n is a p into q, lambda is LCM of p minus 1 and q minus 1. Select any integer g belongs to z and static square. Then and divide the order of g. That is basically we have modular inverse like is mu L of g raised to power lambda, and then mod square, then takes is inverse of this whole under mod n. So L is what you call, if you I can apply L on any u, then u minus 1 divided by, if you can apply L on any input, then it will basically perform operation like that, this expression. If P and Q are equal length, a similar variant of above key generation step would be G can be written as n plus 1, n is phi of n, mu is phi of n inverse mod n, and where phi of n is p minus 1 and q minus 1. So, dear student, so this is one of our what you call the uh, key generation algorithm, and the public key in this case is n and g, and the private key, which is decryption key, which is mu and lambda and mu. So in encryption algorithm, basically it consists of plain text message M and any random number, say R, that belongs to Zn, static. So and set of what you call the plain text is Zn. So I can say the in here the our set of plain text is Zn, and the set of cipher text is Zn square. So the function is over here. If you can see in our last Schmidt crypto system, the domain of plain text and domain of cipher text are not same, but same is the case over here. The domain of plain text is smaller than domain of cipher space, because cipher space is n square Zn square, and the plain text space is Zn. So if you can say the who can compute ciphertext as c is equal to g to the power m dot rn mod n square. So let's see with the ciphertext to decrypt this cipher, which is belongs to z and steric square. So we compute m c l c to the power lambda mod n square, then multiply this result with mu mod of n. So after some calculation and exponentiation, we will get back our message, plain text message m. So these are some of the binomial expression that how your this term is basically how you can calculate L. So if you can say, if you can just take this neglecting the higher power, then this term 1 plus nx power to the power x is equal to 1 plus nx square. So if this is equivalent to y, if I can say this is equivalent to y, this left hand term is equivalent to y, then I just put this equivalent to y, and if I can put this term equivalent to y, then I can solve it for x. I will get x is equal to y minus 1 divided by n mod n. So in that case, dear student, if you can look over here, L of 1 plus n x to the power x mod n square after taking its mod is equivalent to x mod n. So in that case, G is equivalent to n plus 1, where if you can calculate this term, so this will be equivalent to this lambda time m plus into lambda inverse, and this is equivalent to m, because if you can in lambda and lambda inverse all cancel out, and ultimately you will left with m. So let us take one example. Take 2 prime p and q and multiply it with both, you will get n. And take any integer g that is such that the order of g is a multiple of n in zn square. If I can select g is 56, 52, that is 5652. That is, if you take g from this, that 77 square is is quite bigger number. So in that case, you will have to take g, which is a multiple of this. So if you can say the that order of g is basically the order of g, I mean to say, if you can take the order of this g to the power 2310, uh, then and mod it from n square, then you will get 1. So it means to say order of g is 2317, which is multiple of n. The n is over here 77. So 30 into 77 in Zn square. You can take any G was what you call the order is multiple of this n. And I mean to say order of g is the power of g for which you will get identity. So order of g is of uh, order of g is a multiple of n in Gn square. I mean to say you take any element from here was order. It means if you can take the power g to the power 23 10, which is a multiple of this, it will be a identity. So thus the public key for the example is n and g, which is 77, 56, and 52. So I take any plain text from 0 to 77, or 1 to 77, or 0 to 76, or 1 to 77. So I take Zn m from Zn, and take any R from Zn R23. So C is g to the power m r to the power n mod n square. I just perform this calculation, and then to decrypt my ciphertext. So lambda is LCM of 6 and 10. Means to say, if you can go back, so lambda is what? If you can see over here, uh, lambda is this one. So if you can go back, this is lambda is this one, p minus 1 and q minus 1. So you have to calculate it like that. So ultimately, you will have to calculate LCM of P minus and Q minus 1. So P is 7, P minus 1 is 6, and Q is 11, and Q minus 1 is 10. So you'll have to take LCM of 10 and 6, 6 and 10. This is 30. And L of U is, which is, if you can apply L on U, then you will get U minus 1 divided by N. I take it as a sum k. I put it, this expression is equivalent to k. If you can go back into previous slide, and I just want to calculate this expression in order to get my plain text back. So I just take it this as a k. I suppose it equivalent to k. So I just g to the power lambda mod n square L of g to the power 30 mod uh, 59 29. So L of 39 29, if you can apply L on any input, you will get L on u minus 1 divided by n. 30 39 28 minus 1 divided by 77. Ultimately you will perform operation in mod n square, you will get this one. So compute the inverse of k. Why I would like to calculate the inverse of k, because if you can look over here, so I also need this inverse of this lambda, because if this is a what you call lambda, so I also need this, the inverse of that lambda, and I call it as a mu, and k inverse I have to calculate its inverse. So 51 inverse under mod 70 is 74. So my ultimately my uh, plain x, which is m into L of c, uh, L of c lambda mod n square into mu mod n. If you can say what is mu, if you can go back into your slides, so this is my mu here, this one. So how I can get mu? So mu is the LCM of phi of n inverse, or you can say, uh, if I can go back, so this is my mu. If you can see, I can calculate this and take its inverse under mod n. So this is one of the expression for mu. So if you can go back, this one. So this is my mu, basically. I have to calculate first mu and take its inverse, because I take inverse of this whole what you call the expression. So I take inverse because of this, like this expression. This first I calculate this. I call it as a k in my previous in my uh, slide, where I have performed this calculation, for example, and then take it inverse, and it means that I call it this as a k, and it calculates inverse of k, and I call it as a mu. If you can look over here, like this one. So I have to call it as a k, and this is, I need the inverse after calculating all this. I need its inverse. So I calculated inverse under mod 77. So, dear student, this is expression for plain text. C L of C to the power lambda mod n square into mu mod n. So L of 4627 to the power 30 mod n square 77, 74 mod 77. So if I can apply this and apply the modulus to this all expression, the, this is, I have to calculate it with mod 5129. Then ultimately I have to perform all these calculation under mod 77. So I'll get back 42. So this is my final uh, plain text after decryption. And my ciphertext is like this one. This one. So, dear student, this is one of the encryption algorithm that is based on homomorphic encryption. And this is your fourth assignment. Do review and write your own example to understand this idea of homomorphic telling with the Paillier crypto system in electronic e-voting. This is one of the link to understand the basic concept of homomorphic encryption algorithm, how you can implement it in electronic e-voting. I mean to say how to secure electronic e-voting system. Till then, Allah Hafiz. May Allah bless you all.